Hello everyone. Today we'll be going through the derivation of the integrating factor method you probably might have heard of. The reason why I chose this is because when this was being taught in class, I found people, or let alone people, I found myself struggling with how the world does ix equal to e to the power integral px even come in from this thing. So I wasn't able to intuitively follow how this thing worked. So I'll be providing a very short and crisp derivation of how this actually works. So here is it how all begins. The integrating factor method is used when we have something like this, a standard linear differential equation, which is dy or dx plus p of x times y is equal to q of x, where all of them, p of x, y, and q of x are functions. The reason why we have this method is because none of u substitution or by parts or even homogeneous methods work here. Now we begin by multiplying every term by a new function, I of x. Now what does this function have to do? Well, this function, at least for now, has nothing to do with any of these variables. This function has nothing to do with any of them. We simply begin by multiplying I of x with the entire equation. So this gives me I of x times this, I of x times this, and I of x times this.
Now that we have the multiplication out of the way, we move to the next step, which is the product rule. Now I want you to note that this product rule has not been used on this. It is simply a recall thing. I repeat, this has nothing to do with this. So if we have any two functions I and y, then according to the product rule, this is how the derivative would look like. Now if we take this function, call it 1, if we take this function, call it 2, and if we put them right here just below each other, then with simple observation we have that this thing and this thing are the same, and we have to match this one and this one. Now the intuition behind why we pick I of x and why we use the product rule is that we are trying to reverse the product rule. Recall how the integration by parts is essentially a reversal of the product rule. We are trying to replicate the exact same thing here. The problem is that we don't have the product rule explicitly mentioned anywhere. This form does not support the product rule anyhow. So by multiplying a new function, we somehow try to mold our problem into a product rule so that it can easily be integrated. So that is the motivation behind why we equate both of them. Often this step is where people find it intuitively hard to follow as to why both of them were equated. We equated them because we wanted a favorable form. Now that we have them equated, we simply have di of x upon I of x is equal to p of x dx. Then we put the integral sign. Now the LHS is a simple exercise, that is ln of I of x, and we'll let the RHS stay as it is. Now we know that ln of this is simply what power do we raise e to get ln of x. So this translates to e to the power integral p of x dx is equal to I of x.
Awesome. Now that we know from where this I of x equal to e to the power integral p of x dx came from, it is it is a pretty simple thing now. Now since we defined I of x such that I of x times p of x is equal to this one, we can rewrite our equation. So basically, now that we have forced both of them to be equal, we have forced equation 1 to be equal to equation 2. We can now equate any one of the sides to any other. So we choose to equate this part to this part. So equating them will simply give us this equation right here. And then note that this was a reversal of the product rule. And then you simply integrate both sides. So you get the dx removed, and then you have a constant right here, and you put this at the bottom to get the final equation. And this is how you find the general solution. I hope this was helpful. And if there's any suggestions, let me know in the comments. Thank you.